There are a few equivalences that we encounter again and again in sentential logic, and being familiar with them and being able to recognize them with a quick glance will be immensely helpful for your work in this course, and indeed, wherever you have to deal with formal deductive logic. Here, I will discuss them in no particular order. The first one is rather intuitive, and it's called double negation, and it is abbreviated as DN. It goes like this. For any sentence X, X and double tilde X are equivalent. If you need convincing, here's a truth table showing that they always have the same truth value. Some people think of it as the two negations canceling each other, as it were. This generalization, the so-called canceling of double negation, often, but not always, applies to natural languages, like English. So if X is Al smokes, then we know that Al smokes is equivalent to, it's not the case that Al doesn't smoke, which features two stacked negations, where one of them undoes the work done by the other. So if X is A or not B, then DN says that this sentence is equivalent to not A or not B. And if X is this long sentence, then it is equivalent to this other long sentence. In any case, any sentence X prefixed by an even number of tildes will be equivalent to X with 0 tildes. And any sentence X prefixed by an odd number of tildes will be equivalent to not X. The second generalization is a pair of equivalences associated with the name of the 19th century mathematician and logician Augustus DeMorgan. Here's a drawing of him done by one of his students, so you can imagine that not everyone was totally engaged by the lecture. In any case, DeMorgan's laws, as they are called, describe interesting ways in which negation interacts with conjunction and disjunction, and in so doing, they reveal the duality of our V and ampersand operators. We've actually already had the chance to see DeMorgan's in action, and it may even be familiar to you by now. One of DeMorgan's equivalences goes like this. For any sentences X and Y, not X and Y is equivalent to not X or not Y. So this says that the negation of the conjunction is equivalent to a disjunction of negations. Here's a truth table that shows the equivalence. You can also relate it in English to the equivalence between not both X and Y and either not X or not Y. So if you reflect on it for a second, you'll see that Al and Beth are not both going to the party expresses the same as either Al won't go to the party or Beth won't go to the party. Also, this is very important, the generalization says that not X and Y is equivalent to not X or not Y. Not to not X and not Y. Switching the connective is a crucial step here. You can see the non-equivalence in this truth table. And the difference is also apparent in English. If I say Al and Beth are not both going to the party, and you say Al is not going to the party and Beth is not going to the party, we're not saying the same thing at all. You're actually saying something stronger, that is something that is true in a smaller number of situations. What I said is compatible with, say, Al going to the party and Beth staying home, but what you said isn't. For you to be right, both people must stay home. The previous generalization went from conjunction to disjunction, and this one goes in the opposite direction. It says that the negation of a disjunction is equivalent to a conjunction of negations. So not X or Y is equivalent to not X and not Y. Again, here's a truth table that shows that these two are equivalent. At this point, I must also warn you against a mistake that some students make, which is, again, forgetting to switch the connective. So be mindful that not X or Y is equivalent to not X and not Y, not to not X or not Y. This can be shown with a truth table, which you can do yourself. So these two forms clearly do not say the same. Not X or Y is much stronger than not X or not Y. An English instance of the first would be neither Al nor Beth will go to the party. An instance of the second would be either Al won't go to the party or Beth won't. not X or not Y would be true in a situation in which, say, Beth goes to the party, but Al doesn't. But in that same situation, not, parenthesis, X or Y would be false, because at least one of them showed up. So if you want a general but imprecise impression of what DeMorgan laws do, you can think about them in this way. Going from left to right, we have a negation that applies over a whole conjunction or disjunction. Then what DeMorgan does is this. First, it drives the negation inward, inside the parentheses, and distributes it among the two components. Second, it switches the binary connective from ampersand to V or vice versa. Going from right to left, we start with a conjunctive or disjunctive sentence where both of the components are negated. What DeMorgan does is push those negations outwards, outside of the parentheses, and combine them into one tilde. Last, it switches the connective. Also, remember that the rule applies to any sentence that matches the required form, no matter how long. So from left to right, anything that counts as the negation of a disjunction or the negation of a conjunction will trigger the application of this rule. Therefore, not parentheses A and B will be transformed to not A or not B by DeMorgan's because it matches the form X and Y when we substitute X with Y and Y with B. Moreover, not parentheses A or not C is also a candidate for DeMorgan's. You can see that if you substitute X with A and Y with not C, you have a perfect match for the form X, V, Y. Applying DeMorgan's then would give you not A and not C. Likewise, going right to left, anything that counts as a conjunction or disjunction of negations is also game for the application of DeMorgan's. So clearly, not A and not B matches the form not X and not Y. Also, although it might not be obvious at first sight, this sentence fits the form not X or not Y. To see Y, just substitute X with not D and E, and Y with parentheses A and B and not F. When you apply DeMorgan's, you obtained not parentheses X and Y, which, using the same substitution schemes, gives you the following equivalent sentence. Another useful set of equivalences comes under the name of distribution or distributive laws, and if they look familiar to you, there's a reason for that. They are analogous to the distributive laws you had the delight of meeting in your school algebra. Like DM, they also have a left to right and a right to left direction of application. Here they are. For any sentences X and Y, X and parentheses Y or Z is equivalent to X and Y or X and Z. And X or parentheses Y and Z is equivalent to X or Y and X or Z. So in the first one, we go from having a conjunction whose right conjunct is a disjunction to a disjunction of two conjunctions. So we flip the main connective from the ampersand to the V. The ampersand is driven inwards and split into two, so to speak. In the second one, we start with a disjunction whose right disjunct is a conjunction and end up with a conjunction of disjunctions. Again, we flipped the main connective, this time from the V to the ampersand, and the disjunction got driven to the inside of the sentence. Again, I'll let you do the truth tables showing the relevant equivalences. If you look at sentences 1 and 2 here, they're obvious candidates for the distribution law, since we're simply letting X be A, Y be B, and Z be C. So once we apply the rule, in each case we get this. However, sentence 3 also fits the form of the first version, left to right. Just assume that A and B takes the place of X, and then substitute Y and Z with C and not D, respectively. Then, by distributing it, we get this. Likewise, sentence 4 fits the second version of the law, right to left direction. Just assume that not A is X, F or not D is Y, and not G is Z. Here are some exercises to test what we've learned so far. First, let's see if you can recognize correct applications of rules. Suppose that I went from 5, which is not parenthesis, not A or B, to 6, which is simply A or B, or vice versa. Would this be a correct application of DN? Think about it for a second. No, this wouldn't be a correct application of double negation. 5 is not the right form to trigger the application of the end, since it is not a doubly negated formula. That is, it is not of the form tilde tilde x. Sure, there are two tildes, but the second one does not occur immediately after the first, since there is a parenthesis in between them. Rather, what we have here is a negation of the sentence not A or B. If you look at it right to left, A or B is of the right form for the n, but the result of this application would be tilde tilde, open parenthesis, A or B, close parenthesis, with two consecutive tildes, which is quite different from not, open parenthesis, not A or B, close parenthesis. What if I went from 7 to 8 and justified this by a single application of DeMorgan's? Would this be correct? Yes, it would. The relevant form of the rule would be not x and y to not x or not y. You can see that because we're going from the negation of a conjunction to a disjunction of negations. Moreover, you can check that everything fits. If you substitute x with A and y with B and C, you can see that 3 fits perfectly the left-hand side of the rule and 4 the right-hand side. And what if I had 5 and then obtained 10, where my justification would be a single application of DeMorgan's? Would this be correct? Let's check. 9 is, in terms of its form, a disjunction of negated sentences, so it would fit this version of DeMorgan's, namely not x or not y. To see this, substitute x with B or D and y with F, and we get our sentence 9. But then, when you apply DeMorgan's here, what you get is the negation of a conjunctive sentence, and this is where 10 doesn't fit, since it is the negation of a conjunctive sentence. So this purported application of DeMorgan's is wrong. You can't go from 9 to 10 or vice versa through an application of DeMorgan's. Okay, this is all for this video.